Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1848 marks a pivotal point in the history of thermodynamics, a year in which William Thomson, later Lord Kelvin, published his seminal paper on an absolute thermometric scale. This work transcends the limited scope of mere temperature measurement. It establishes a profound conceptual framework that reshaped our understanding of heat, energy, and the very foundations of physics. To appreciate the magnitude of Thomson's contribution, one must first examine the intellectual landscape that preceded it, the specific challenges faced by physicists of the time, and the ingenious manner in which Thomson addressed them. Prior to 1848, thermometry was largely an empirical endeavour. Temperature scales, such as Celsius and Fahrenheit, were based on the readily observable properties of specific substances, most commonly the expansion of mercury. These scales, while practically useful, suffered from a fundamental limitation. Their 0 points and unit sizes were arbitrarily defined, tied to the characteristics of a particular material under specific conditions like the freezing and boiling points of water. This led to considerable ambiguity and difficulty when comparing thermal phenomena across different experiments, or when attempting to formulate universal laws of thermodynamics. There was a pressing need for a temperature scale grounded in absolute physical principles, independent of the idiosyncrasies of any particular substance. The development of thermodynamics itself was still in its nascent stage. Sadi Carnot's groundbreaking work on the efficiency of heat engines, published in 1824, provided crucial insights into the relationship between heat and work. However, Carnot's analysis relied on the caloric theory, a now discredited idea that heat was a conserved, weightless fluid. While Carnot's conclusions regarding the limits of engine efficiency remained valid, their theoretical underpinning was flawed. The first law of thermodynamics, concerning the conservation of energy, was beginning to gain traction, largely due to the work of James Prescott Joule, Julius Robert von Mayer, and Hermann von Helmholtz. Their experiments demonstrated the equivalence of mechanical work and heat, suggesting that heat was a form of energy rather than a distinct substance. Thomson's genius lay in recognizing the significance of Carnot's work while simultaneously acknowledging the limitations of the caloric theory. He sought to reconcile Carnot's principle with the emerging understanding of heat as a form of energy. In his 1848 paper, Thomson proposed a new thermometric scale based on the efficiency of an ideal heat engine, a theoretical engine operating in a reversible cycle. As described by Carnot, this ideal engine, unlike real-world engines, operates without any energy losses due to friction or other irreversible processes. The absolute thermometric scale, as envisioned by Thomson, possesses the unique property of being independent of the working substance used in a heat engine. The efficiency of a Carnot engine depends only on the temperatures of the hot and cold reservoirs between which it operates. Thomson reasoned that if one defines temperature such that the ratio of heat absorbed at the high temperature to the heat rejected at the low temperature is solely a function of those two temperatures, then one obtains a temperature scale that is truly absolute. Mathematically, this can be expressed as follows. Let Q sub 1 represent the quantity of heat absorbed by the engine from the high temperature reservoir, and let Q sub 2 represent the quantity of heat rejected by the engine to the low temperature reservoir. Let theta sub 1 and theta sub 2 represent the temperatures of the high and low temperature reservoirs, respectively. On the new absolute scale, Thomson proposed that the ratio of Q sub 1 to Q sub 2 is a function solely of theta sub 1 and theta sub 2. By choosing a suitable functional form, specifically setting the ratio Q sub 1 over Q sub 2 equal to theta sub 1 over theta sub 2, Thomson defined a temperature scale where equal intervals correspond to equal changes in the ratio of heat absorbed to heat rejected. The crucial implication of this definition is that the 0 point of the absolute scale corresponds to the temperature at which a Carnot engine would have 100% efficiency, meaning all the heat absorbed would be converted into work. This 0 point, later known as absolute zero, represents the lowest possible temperature, a state where all thermal motion ceases, at least according to classical thermodynamics. A temperature below absolute zero would imply an efficiency greater than 100%, violating the laws of thermodynamics. Thomson initially called his scale the thermodynamic scale, but it later became known as the Kelvin scale in his honor. The Kelvin scale is directly related to the Celsius scale, with a difference of approximately 273.15 degrees. Thus, 0 degrees Celsius corresponds to 273.15 Kelvin. This offset ensures that the size of the degree is same on both scales. While the 0 point of the Kelvin scale is truly the immediate impact of Thomson's work was profound. It provided a rigorous foundation for thermodynamics, Unifying the principles of Carnot and Joule into a consistent framework, it allowed scientists to compare thermal phenomena across different experiments with unprecedented accuracy and confidence. The absolute thermometric scale quickly became the standard for scientific measurements and calculations, replacing arbitrary scales that had previously been used. Despite its initial success, Thomson's absolute thermometric scale encountered some initial resistance and required further refinement. The concept of absolute zero, in particular, was initially difficult for some scientists to grasp. It represented a theoretical limit that could never be reached in practice, a concept that seemed almost metaphysical to some. Moreover, the precise determination of absolute zero required careful experimental measurements and extrapolations, which were subject to uncertainties. Over the years, Thomson and other physicists continued to refine the experimental determination of absolute zero, using increasingly sophisticated techniques. One crucial advance was the development of pulse thermometers, which measure temperature based on the pressure or volume of a gas. By extrapolating the behavior of gases to very low temperatures, scientists were able to obtain more accurate estimates of absolute zero. However, even gas thermometers have limitations, as real gases deviate from ideal behavior at low temperatures. The development of quantum mechanics in the early 20th century provided a deeper understanding of the nature of absolute zero. Quantum mechanics reveals that even at absolute zero, atoms and molecules possess a minimal amount of energy, known as zero-point energy. This zero-point energy arises from the Heisenberg uncertainty principle, which states that it is impossible to know both the position and momentum of a particle with perfect accuracy. As a result, particles are never perfectly still, even at absolute zero. Despite these quantum mechanical nuances, Thomson's concept of absolute zero remains fundamentally valid. It represents the lowest possible temperature that can be approached, even it cannot be perfectly attained. The Kelvin scale continues to be the standard for scientific measurements, playing a crucial role in fields ranging from cryogenics to astrophysics. Thomson's 1948 paper influenced the work of numerous scientists. Rudolf Clausius, for example, built upon Thomson's ideas to develop the concept of entropy, a measure of disorder in a system. Clausius' work, in turn, led to the formulation of the second law of thermodynamics, which states that the entropy of an isolated system always increases or remains constant. The second law has profound implications for the direction of time and the ultimate fate of the universe. James Clerk Maxwell, another prominent physicist of the 19th century, incorporated Thomson's absolute thermometric scale into his kinetic theory of gases. Maxwell showed that the average kinetic energy of gas molecules is directly proportional to the absolute temperature. This relationship provided a microscopic interpretation of temperature, connecting it to the motion of individual particles. The legacy of Thomson's work extends far beyond the realm of pure science. The Kelvin scale is used in many practical applications, such as the design of engines, refrigerators, and other thermal devices. It is also essential for understanding and predicting weather patterns, climate change, and other environmental phenomena. Moreover, the concept of absolute zero has inspired countless works of art, literature, and philosophy, serving as a metaphor for ultimate coldness, stillness, and the absence of. In retrospect, Thomson's on an absolute thermometric scale stands as a testament to the power of theoretical reasoning and the importance of absolute standards in science. It showcases how seemingly abstract concepts can have profound practical implications, and how a single insightful paper can transform our understanding of the world. The establishment of the Kelvin scale was more than a mere refinement of thermometry. It was a crucial step in the development of thermodynamics and a cornerstone of modern physics. It is a reminder that the pursuit of absolute truth, even in the face of uncertainty and complexity, is a hallmark of scientific progress. It is difficult to overstate the impact of Thomson's work on subsequent scientific endeavours. Consider, for example, the field of low-temperature physics, or cryogenics. The development of technologies to reach extremely low temperatures, approaching absolute zero, has enabled scientists to explore a wide range of novel phenomena, such as superconductivity and superfluidity. Superconductivity, discovered in 1911 by Heike Camelingons, is the phenomenon in which certain materials lose all resistance to electrical current at very low temperatures. Superfluidity, observed in liquid helium at temperatures near absolute zero, is a state of matter in which the fluid flows without any viscosity. These discoveries would be unimaginable without the precise temperature control afforded by the Kelvin scale and the conceptual framework provided by Thomson's work. Furthermore, Thomson's insistence on an absolute standard for temperature paved the way for a more rigorous and unified approach to other physical measurements. The development of the International System of Units, or SI, which is the modern standard metric system, owes a significant debt to Thomson's emphasis on absolute scales. The C system defines fundamental physical quantities, such as length, mass, time, and temperature, in terms of invariant physical constants. The Kelvin scale, as defined by the triple point of water, an integral part of the system, ensuring consistency and comparability across scientific measurements. While the process of arriving at the modern definition of the Kelvin scale itself is a fascinating example of scientific refinement and international collaboration. Initially, the Kelvin scale was defined based on the freezing point of water and the boiling point of water. However, as experimental techniques improved, it became clear that the triple point of water, the unique temperature and pressure at which water can exist in all three phases, solid, liquid, and gas, in equilibrium, was a more stable and reproducible reference point. In 1954, the International Committee for Weights and Measures adopted the triple point of water as the defining fixed point for the Kelvin scale, further solidifying its status as an absolute standard. The value of the triple point of water is defined as exactly 273.16 Kelvin. Even with the adoption of the triple point of water as the defining fixed point, scientists continued to strive for even greater accuracy and precision in temperature measurements. In recent years, there has been a move towards defining the Kelvin scale in terms of fundamental physical constants, such as the Boltzmann constant. The Boltzmann constant, denoted by K sub b, relates the average kinetic energy of particles in a gas to the absolute temperature. By fixing the value of the Boltzmann constant, scientists can define the Kelvin scale independently of any specific substance or phenomenon, making it truly absolute in the most fundamental sense. The current best estimate of the Boltzmann constant, obtained through sophisticated experiments and theoretical calculations, approximately 1.38 times 10 to the minus 23rd joules per Kelvin. The ongoing efforts to refine and redefine the Kelvin scale highlight the enduring importance of Thomson's 1848 paper. It is a testament to the fact that even the most fundamental scientific concepts are subject to scrutiny, revision, and improvement as our understanding of the universe deepens. It also underscores the collaborative nature of scientific progress, with scientists from around the world working together to establish and maintain standards that ensure the accuracy and reliability of scientific measurements. Thus, William Thomson's contribution extends far beyond the creation of a mere temperature scale. It embodies a commitment to absolute standards, a pursuit of rigorous scientific understanding, and a legacy that continues to shape the course of scientific progress. His 1848 paper remains a cornerstone of thermodynamics and a shining example of the power of human intellect to unravel the mysteries of the universe.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.